Welcome everyone to the final talk of the conference. So I hope everybody's still excited and interested and engaged and ready to go to talk about architecture as code.
Hey, fantastic. My name is Mark Richards. And
I'm Neal Ford, as you probably guessed.
Yes, and before we get started on our last session, I did want to just reach out and really thank Square and all of the sponsors for making this community happen. This has been going on strong for so long, and let's keep it going for years to come. So thank you, Square, and the sponsors. Thank you. Awesome. All right. So you follow all of the star ratings in our book, The Fundamentals of Software Architecture, to do qualitative analysis to determine the best architectural style. You then do modern trade-off analysis that we described in our book, Architecture, the Hard Parts, and make all the right decisions. Yet architecture still doesn't seem to work. There's one more ingredient, and that's what we're going to show you today as architecture as code. We're going to start with two premises. The first premise, architecture doesn't live alone. It doesn't live in a silo. Rather, it must be aligned with other aspects of our technical and business environment in order to be successful. And we call these the intersections of architecture, or more formally, architectural nexus. A nexus being plural of nexus, which is an intersection. In order for architecture to work, it has to be aligned with implementation, infrastructure. It has to be aligned with data topologies, engineering practices, and yes, even our team topologies. It has to be aligned with other systems in our environment that we interact with. It has to be aligned with the business, the enterprise, and finally, generative AI. Now, we're going to take a journey of all of these intersections in this last session. But before we do that, we have one other assertion we need to make.
So Mark and I have been talking about these intersections for a long time. Architects have a unique perspective on software projects because we can see all of these things. We can see how things are going to be implemented. We understand the infrastructure. We understand the business capabilities. And one of our jobs is to govern the software that we build. And in fact, I wrote a book several years ago called Building Evolutionary Architectures, which is this idea of automating architectural governance using this idea of architectural fitness functions. And that lets you check to validate that the structure is correct, that the design that I created as an architect is in fact being implemented correctly by developers. But you can also check operational concerns, which we'll show you an example of, and even process concerns like how we use version control, because that impacts your architecture as well in an example that we'll show you. As I said, Mark and I have been thinking about these intersections for a long time, but what we struggled with was how do we describe these intersections in a way that's not just a lot of words, because we don't really need a lot more words to describe these things, and that's exactly how we're going to describe all of these intersections is with code, and specifically with architectural fitness functions. That's how we're going to describe each of these intersections with software architecture as code, as a way of definitively defining the goals and the designs that we want in our software architecture. Why are we doing this? Well, it's nice to be able to create a design and validate that design and make sure it works, but what we really want out of this is super fast feedback on important structural changes. Because if you're in Java, like our last speaker was, and you create a new directory as you're implementing a solution, you've created a new package in Java, which is a new component. That's an architectural element in your code base. But what if you as the architect don't find out that that developer created that for 6 months, they've changed your overall design, and you didn't find out about it until maybe it was too late to make a change? What we're talking about is a way of generating fast feedback on important structural changes. And every one of the examples we show you today are examples of that fast feedback. And what we're trying to do here is, if you look at before Agile engineering and the way we tested our domain, we tested it, but it was spotty and in places and sometimes arbitrary. And what Agile taught us was we need comprehensive testing for the entire development process. And in fact, now for our testing, we have unit and functional and user acceptance testing and quality assurance if your company is big enough. But for our architecture characteristics, our important architecture concerns, we have spotty and inconsistent testing, just like we did before in Agile in our domain. What we're trying to do here is actually give us the same level of confidence that our architectural structure is in fact giving us fast feedback on changes, just like we've become accustomed to as we build our problem domain.
All right. Well, to describe architecture as code, Neal, Ford, and I developed what's called an architecture definition language, an ADL. This is a pseudo code language that's used to describe these various intersections of architecture, but not only describe these, but also ensure that alignment, validate that we are in fact aligned, or tell us when we're not aligned. This ADL, which we're going to be looking at as architecture as code includes metadata, just that's kind of information about this test I'm about to write, all sorts of artifacts as well, in terms of libraries, domains, subdomains, components, and then finally, actions. In other words, assertions that we can make about that particular constraint. Now we can take this architecture definition language and we can now utilize this. I can use Gen AI to be able to generate structural code in any of these frameworks. I can also use this to describe the kind of monitoring I need for my particular system through observability tools, or even write my own custom fitness functions. We're going to see examples of all of these in this session. But let's start with the one that probably is most interesting to most of you, and that is the intersection of architecture and implementation, and that corresponding alignment. We look around at this building around us, we see there's a lot of spans of metal. There's load-bearing walls. There's weight. There's a lot of architecture to this building that I'm looking at here. That's what an architect does, is describe how this building, the structure of this building, should be used. That's what a software architect does as well. So we bring in a bunch of craftsmen, masons, and they build this structure we're in now. Let me ask you, did they build it directly to that architecture? I hope so. We all hope so. How many times have we wondered, is the implementation of our software actually representative of that structure that we spent so much time defining? We can use architecture as code, which we will, to be able to generate code in either things like ArcUnit for Java, TSArc for JavaScript and TypeScript, ArcUnit.net, NetArcTest for both of those in C#, and also even PyTestArc for Python. Yeah. So let's see an example of this, because like the building right here, this happens to be an architecture for a trouble ticket system, where our customers, if they have issues, go into the website, create a trouble ticket, and we process it. We find an expert in the field, they come to their home or office, they fix the problem. We spent a lot of time on this architecture to promote agility, extensibility, reliability, evolvability, and even, maybe even for migration. So, how can I ensure this alignment? I can write architecture definition language to say, first of all, Let's define our system right here. And now I could describe my domains. I could define domain ticketing, define domain customer, and I can define my domain survey. How many times have we done domain-driven design and spent all that effort, and then we say, that was fun, now I got a great understanding of what we're building. Let's code. Have you ever gone back in the code to actually see where those domains, subdomains, bounded contexts actually are? Because here, I can now assert that all code is contained within those domains and subdomains below it. As a matter of fact, I tie this ADL to the physical location in the directory structures or namespaces of where that code resides. Now, I can feed this into a Gen AI, for example, ChatGPT. It says, this is what I think you're trying to do, and here's the code it generates. Executable source code that describes my architecture. This is it in C#. I can show you Python, I can show you JavaScript. This is pretty amazing. As a matter of fact, we can go as far as to even describe those domains. For example, our ticketing domain contains a lot of components. What does it contain? It contains ticket creation, ticket completion, a ticket queue, and also a subdomain, assignment, to assign those tickets. I can assert that all classes are under those defined components. I link that to the corresponding code, run Gen AI, and now I have executable source code. Oh, before Neal and I started this research last year in this architecture as code, I was writing this code all the time. I was writing ArcUnit netcode all the time. But that's a description of my architecture that's a little harder to read than the architecture definition language. But this everyone, is only one of the intersections that describe the structural aspect of architecture.
Talk about the intersection of infrastructure and architecture. So I have a product owner who says things like, the order submit API must scale to 5,000 concurrent customers with an average response time of 600 milliseconds under load. And the architect says, okay, no problem. Got it, that's our requirement. Where's that information documented outside of this conversation? Maybe you wrote it down in an ADR somewhere, an architecture description record, to document that, but where do you validate that? How do you make sure that that is actually true after the fact? What we want is another level of documentation between the words that are spoken in a conversation and even documentation for it, something that is actually executable. So we can express this in our lightweight architecture definition language, which is meant to be very flexible and malleable. And we can assert these goals for our architecture, assert that response time is under a certain response time, et cetera. And now we can write fitness functions to validate that, or wire up monitors and other mechanisms to look at that. And what we want to see here is not only that the business's goal was met, but we can validate that the business's goal was met. So as the number of concurrent users gradually rises, you can see the average duration, request response time per user. What we want to see in that architecture is as the number of concurrent users go up, my average duration per user stays nice and flat. And in fact, if that does start tilting up, I want to know as soon as it starts tilting up, not when it hits some sort of emergency spot. This gives me really, really good feedback on exactly what the operational characteristics of my architecture are.
Aside from implementation, perhaps the other biggest use of architecture as code is actually for data topologies. There are so many tests, verifications that we can run that can verify our consistency, our integrity, data loss, to make sure all of our data pumps are asynchronous, that reporting systems are not actually truly accessing our transactional systems, database performance, connection weights, even our transaction scope. All of this I can measure. And here's a good example. So I, as the architect, made a decision to physically break apart our database into 2 domains. And that gives us better fault tolerance, better change control, and better scalability. It's a good justification. This is a lot of times why we break up data. Now, our product owner says, that's great, but you better make sure you don't lose any trouble tickets. And both those domains are in sync with each other. Okay, I'm on it. By the way, where is this documented? And how do we even verify this? So this kind of decision is typically documented through an architecture decision record. But where's the validation? Where's the measurement? Where's the description? That's where the ADL comes in. The architecture definition language, architecture as code, can describe this constraint. And as a matter of fact, this particular clicker doesn't work here. I'll move over here. This describes our data consistency, in which now that I have that description, it's part of our architecture. I can now write a fitness function to govern this. Here's our 2 domains. Notice the 2 separate databases now. What I can do is I can certainly count the number of tickets in this database over here. I know how many tickets are pending, and I also know how many I've processed. And what I can do every hour is just wake up and make sure that the count of tickets in that database is equal to the number I sent and the number I processed. I can do a hash of the keys to verify that I have foreign keys. Well, they're not foreign keys anymore, but logical foreign keys matching all my primary keys within the other database.
Yeah, we are familiar with the idea of eventual consistency in microservices, but we have eventual all the things in databases. We have eventual referential integrity, we have eventual cascading deletes. You can build all those things with architecture fitness functions and restore the behavior that you're used to from a relational database in your code. Most of the ones we've been talking about so far are pretty obvious, and you'd kind of bump into those if you were thinking about automating governance anyway. But let's talk about a more interesting intersection with engineering practices, because again, this is one of those things that has an impact on architecture because all these things are sort of synergistically tied up with each other. Things like version control and automated testing, code cleanliness is obviously a governance of concern. In fact, many of you are already doing this, you just don't call it this yet. You're already using something like SonarQube, or you've got some metrics tools wired into your continuous build. That is the baby steps toward exactly this process we're talking about. But let's talk about version control for a second. Because as architects, we often are forced to make decisions that have no real good outcomes. Because one of the choices you often have to make is, should we use a mono repo or should we use a repo per service? And the problem with that decision is that both options suck. The problem is they suck in different ways. And now, as the architect, you have to decide for our project which one sucks less. That is very often your job as the architect, is not find the best solution, but find the least worst solution to a problem, the one that sucks less for what we're looking for, but the suck is still there. And so how do you mitigate the suck when you make one of these choices like this? So for example, let's say we've chosen mono repo. We've looked at all the trade-offs. Okay, we're going to use a mono repo, but it still sucks in a very particular way. So what's the big danger in a mono repo? Cheating on dependencies. It's all right there. I'm a developer. I'm almost finished with this task. One last thing to do, and I've got to write this method, but oh, look, there's already one up there. It's exactly what I need, but it's just right there. One import, and I'm done. I could finish off the day, and it's just so, that one, I've got to write a whole, it's just.
Don't do it, Neal. Don't do it.
It's just
Don't
so
do it.
tempting. It's this. So how do you prevent that from happening? Well, this is an architectural concern. And so you can manage this from architecture. So this is a microservices architecture, which is mostly free of dependencies except for the one sleep service, which has explicit dependencies, now I can build a fitness function that asserts that all these dependencies exist, and then write a fitness function that validates that no one is cheating on my dependencies. So that cheating in the monorepo reflects in the source code that you're building in an import that shouldn't be there. If I restrict that import from happening, I've now solved the negative aspect of a monorepo, and I can use that engineering practice with confidence, knowing that the weak points of it that can cause damage to my project, I've governed and made sure it's not going to cause damage. There we go, yeah.
In order to make architecture work, it also has to be aligned with our team topologies. Whether those teams be partitioned by technology or by domain, or perhaps we go as far as to even use the categories described in the team topologies book. Are the team structures that we put together aligned with our architecture and our architectural goals? And vice versa. Can the architecture even be created or even supported by this kind of team structure? Well, let's take that ticketing problem example, and let's actually take a look at some team topologies here. So we decided that we have a whole administrative portion of that sysup squad ticketing trouble ticket system. So we created a stream-aligned team to focus on all the features within admin. We decided to create a stream-aligned team for ticketing. Now, these teams are meant to really focus solely on the functionality, the behavior of that system, without any problems or bottlenecks. But we do have one problem, and we do have one bottleneck. Assigning tickets is hard. That's like the traveling salesperson problem. And so consequently, we decided to create a complicated subsystem team from the team topologies for that expert assignment. Perfect. How do we know that that's the right team structure? One way, are these teams getting in each other's way? How do we know if they are? Well, I suppose one metric we can gather is when I create a Jira ticket for a particular feature, how many tickets am I actually creating for the number of teams we have? And that might be one metric. But another one that really helps validate our team structures in coincidence or in coincidence with our architecture might be merge conflicts. It's a great metric. If teams are struggling and stumbling and getting each other's way, a lot of times we can see that through merge conflicts. And so let's put some parameters in place. We expect less than 5% merge conflicts between our two stream-aligned teams. I expect 0 merge conflicts between our complex subsystem team and admin. These have nothing to do with each other. And I'll accept at least up to 10% merge conflicts here. Great. How do we measure this? How do we ensure this kind of alignment? Architecture as code. Because now I can describe these merge conflicts in my architecture definition language. I can describe the actors, the players, the teams that are involved in this architecture. Notice I've defined 3 teams, 2 stream teams and 1 complex subsystem. And I assert that the merge conflicts are a certain percentage between those various teams. Now this is cool because I can either write or generate the corresponding Git code to capture, measure those merge conflicts, calculate those, and alert me if we have a problem or fail that test. Is that cool? We can actually run tests for our processes and even our team structures because our architecture has to be aligned with those and vice versa.
In fact, this is a great example. One of our mantras in the architecture as code world is what data do I need and where
Yes.
does it live?
Yes.
And this is a great example of what data do I need? I need to know how teams are interacting with each other. Where does it live? It lives in version control because that's who knows how teams are interacting with each other. So it's a great example of
Yes. Words
finding
to remember.
Exactly. Yep. What data do I need and where does it live? System integration is obviously another place where we can do a lot of architecture as code, and this touches on a lot of areas of integration. There's some specific metrics we can look at. There are fitness functions for event-driven architecture. There are observability, which is one of the superpowers in an architecture like this. Conflict-free data types, conflict resolution-free data types, CRDTs. It's a hard thing to say, which is why it's an acronym. Is a way of designing auto-mergeable data types, so you don't need a central server somewhere. They automatically resolve themselves. So that's an interesting sort of architecture as code idea of preventing merge conflicts by designing them so that they can't happen. But let's talk for a second about analyzing your architecture using this idea. Let's say you have, this is our ticketing system, and this is our architecture with the dependencies between things defined. So in other words, customer user interface depends on ticket creation, ticket completion relies on ticket creation. I want to be able to find what these dependencies should be in my architecture so that if somebody creates a dependency I don't want, I should know about that right away. And this also lets me both define those things and make sure that all the dependencies in my system exist between those things I've named and be able to create concrete code from it. But if I have this information in things like logs, I can also use this to do analysis on my architecture. So for example, I can say, given these log entries where the first entry is the service and everything else are dependencies, draw a directed graph of the dependencies in this system. Give this to generative AI, and sure enough, there's a directed graph. And I can also ask it, what's the longest chain of dependencies in this system, which is the thing on the bottom. So if you look at my actual diagram and what Gen AI generated from just the log entries, they match each other. That is basically the same view of that architecture. And as you can see, the longest dependency chain between these is UI to creation to assignment to mobile app to completion. This helps me identify fragile parts of my architecture because these really long dependency chains, if one thing breaks, all of those things break. And so you can use this to analyze how things are wired together in your architecture. I keep forgetting to go to there we go.
Well, we can't forget about the business. Yes, our architecture also has to be aligned with our business environment. Let me show you what I mean. Here's that architectural characteristic star rating that we created for our fundamentals book. It allows for qualitative analysis of what architectures lend themselves better towards certain characteristics and capabilities, and which ones don't. Where 1 star, that characteristic isn't well supported. Oh, can we maybe do some things to compensate for it? Maybe. But it's not really well supported. Whereas 5 stars, very well supported. Now, it's interesting. The architectural characteristics, these capabilities, point to which architecture style might be most suited for us, which would align best to those capabilities. But where do those capabilities come from? And they come from the business and the business environment. So let me show you what I mean. When I say about the business environment, is your business currently undergoing some pretty severe cost-cutting measures? Or is it aggressively expanding by mergers and acquisitions and opening up stores everywhere? Do you have to undergo regulatory compliance? Or maybe it's simple competitive advantage to remain alive in this really highly competitive market we have today. Do you have a small business or a very complex or large business? Is it pretty straightforward or really complex? And is your business undergoing constant change? These are all aspects of the business. Businesses, everyone, 20 years ago, 30 years ago, changed. Oh, they pivoted. They reacted to market conditions. But those reactions were usually measured in years. Today, they're measured in months. Months. It's all of us, unfortunately, sitting here in this room and standing up on stage that now are the bottlenecks for businesses to be able to react and pivot fast enough in this market. Let's change that. So let me show you an example. Let's say our business is undergoing aggressive expansion in the market. Well, that really equates to having high levels of scalability, interoperability, and also to be able to evolve our architectures. Those are the capabilities that match aggressive expansion. What type of architectures align well to those? Not surprisingly, distributed architectures. These in particular, microservices, even service-oriented. Let's not say that word. Let's remove that one, Neal. Event-driven and even space-based. These align well, and we're well positioned for the business to be able to do what they need to do. But these ones are not. That poses risk that we have. So what we can do is write architecture as code that describes this kind of business movement. The characteristics we need are scalability, extensibility, and operability. And we assert that the system must exhibit these defined characteristics. What use is this architecture definition for? It tells us exactly what we should be measuring and analyzing to ensure that business alignment. And we can do that through custom fitness functions or even operational and observability tools. A couple more to go.
Next one is about enterprise. And in fact, this one has a specific role of enterprise architect assigned to it. This is a mind map that one of my colleagues created at one point of the potential responsibilities for enterprise architects. And this covers a lot of ground, things like business engagement, technology platforms, decisions, long-term strategy, automated systems, IT operations, and the organization, all of those things come under the purview of enterprise architects. And obviously all of these give you places where you can express these goals in code. We talk about many of these for things like zero-day security checks to make sure that you know exactly what software is running in your system, global coding standards, software bill of materials. If you're not using that now, you're going to be using it, because AI provides a lot of new attack vectors for our software systems that we need to be able to react to really quickly. Again, it's about really super fast feedback to important things. And so the enterprise here can define things like, we need a standard security library that is for all of these services, that has a certain version number, and we can guarantee compliance. And we can do this across platforms. So this is one of the advantages of ADL as a pseudocode, is we can use this to generate Java JUnit test, ArcUnit. We can do .NET tests or Python, have one source of truth, but then generate the actual fitness functions to validate those things for us. And the last one, of course, we can't do a talk about technology in 2025 without talking about generative AI. That is required, but that is an important intersection now to architecture. But to architects, AI is a big giant black box, and we need to avoid cracking open the black box because there's a lot of delicious complexity there. Instead, what we care about is the ecosystem and productionalizing AI. And that's going to be things like patterns and observability and structured outputs. But the two main areas of intersection are things like evals and guardrails. Guardrails are ways that we control the behavior of the LLM, the inputs and the outputs, filtering around data and other sorts of concerns like that. And so now we can build For example, for our make the grade system, we want to use AI graders. We want to make sure that the manual grader and the AI grader come up with similar results, at least within a threshold, to make sure that AI is doing a reasonably good job of this task that we are trying to move from manual grading. We can assert that and write fitness functions to validate that, and also do manual verification, which is an important point to make here. Not all of these fitness functions are going to be automated. Some of them need to be manual in a case like this, but it's still a way of getting fast feedback on a critical infrastructure piece of my ecosystem.
Yeah. Fantastic. So in the session, we showed you 3 concepts. The fact that architecture does have to be aligned in order to work. We showed you this concept of architecture as code, where we can actually describe our architecture as executable source code that can ensure those alignments. And we also gave you a very valuable tool, a tool to be able to provide fast feedback when things do become misaligned or break. So I hope you very much enjoyed that. Thank you all so much. Thank you.
Thank you.